Welcome everyone. So today we are starting our section on forces. I'm very excited, and we're going to start with one. We're going to say one with the force. Let's see how we do. So we're going to start with a couple of questions. The first one is, what is a force? Well, hopefully we've got some ideas because we've done a little bit before in our younger grades, hopefully, but sometimes we've got to think about it and it's not this ethereal thing. But what is a force? What makes something a force? And then, do all moving objects experience a force? Do all stationary objects experience a force? So as I'm standing here talking to you, am I experiencing forces? Or just one force? Or lots of forces? So that's what we're going to look at today. Okay? So, starting with our map, and we're going to look at all the different concepts. So we're going to go through all of these in this section. We're going to look at the properties of a force. We're going to look at what types of forces we have. How do we represent a force? Because that's very important. What are the components of a force? What is friction? How does it work? Forces and motion or non-motion, depending on the section. And then, of course, Newton's second law. That one's very important, okay? That's going to come up lots. So, let's go to what our key words are. Force, so we're going to need to define it. What is a force? Where do we know what it does? What is a contact force? Very important. What is a non-contact force? And then, of course, newtons. Okay, so those are our units. And the spelling there is quite important. So, let's start. We're back here. What we're going to look at now is we're going to look at properties. What makes a force a force? Okay, so that's quite important. So, at the beginning, first of all, we need to define what a force is. Well, a force in its very, very simplest form is a push or a pull. So when we push something or we pull something, we're exerting a force, okay? All forces are either a push or a pull. Sometimes that means an object's going to move, sometimes it means it isn't. It all depends on the force, okay? What do we measure force in? Well, force, the unit is named after Isaac Newton, who you've probably heard about before, okay? And the unit is the Newton. It's spelled with a capital because it's named after a scientist, okay? And because it's named after a scientist, it has to be a capital, and it's a capital N. Now, please be careful when you write this one. This one's quite important. So when we write this, be careful that you don't write it as a round N, because that can sometimes look like a lowercase, and it's very much a capital. So when we write, it's got to be a capital letter, okay? So, back here, now what we're going to do is we're going to look at the types of forces. So we know it's a push and a pull, but not all forces are the same. It all depends on the things that are involved. Forces need objects, okay? They involve objects. There are always two objects involved. So, first one is our contact forces. Now, contact means they must be touching, okay? So it's forces where the force gets exerted because two things are touching each other. They have to be touching, okay? You've seen different types. We get applied forces. Now, applied forces can be from all sorts of things. So an applied force, for example, is when I push from one hand to the other hand, I'm applying a force. It's a pushing force, okay? So it's applied. Tension is the force we get between a rope. So if we're going to look at a little bit of a tug of war later, and if I have a rope and I'm pulling on both sides of the rope, that's tension in the rope, okay? Or, you know when you're naughty in class and you take an elastic band and you stretch it so you can shoot it at someone, don't do that, it's bad. But when you stretch it, you get tension in the elastic band. That's tension, okay? Friction, such an important force, this one. We're going to spend lots of time on it. Friction, like when you rub your hands. Okay, so it's contact. You only get friction when there's contact. Now, friction, we get friction like on surfaces, and then we get air resistance. Air resistance is also friction, and then you're going to go, but where are the objects? Well, the air is made out of particles. The air has particles. When those particles touch whatever's going through the air, we get air resistance. That's still friction, still contact. Then we get the normal force. Ooh, hopefully you've come across this. Okay, hopefully in your younger grades you've come across the normal force. This is also another important one, and we're going to spend time with that a little bit later on. But the normal force is always between a surface and an object. Okay, so I'm standing on the floor right now, and the normal force is acting up on me. Okay, because I'm pushing down on the floor. So me and the floor of contact, I push on the floor, contact force. The floor's pushing up on me, contact force. That's the normal, okay? Then we've got non-contact forces. Now, these go on to, sometimes we also call these field forces. So hopefully you've seen those, okay? Field forces, we're not going to spend too much time on field forces in this section, okay? The first one, well, we have a few here, okay? So we have gravitational, that we all know about. We're very happy that we have gravitational forces because, well, we wouldn't be on the earth if we didn't, okay? So the first one is gravitational. The next one is magnetic. You've spent some time doing magnetic forces, okay? When you have two magnets next to each other, yes, they can be in contact, but when they're a little distance away from each other, the force between them still acts. So they still feel they're a non-contact. They don't have to be touching, okay? Then there's the electrostatic forces. I can hear the groans from when you did electrostatics before because you didn't like it. Electrostatic forces between charged objects. Yes, they can still touch, but they don't have to be touching. Okay? Same with gravity. Okay, yes, we are on the surface of the earth, but if I jump into the air, I'm not touching the earth, but there's still the gravitational acceleration. So they don't have to be in contact. Okay? So, how do we represent a force? Here again, it's remembering that force is a vector. As a vector, it has size and direction, okay? So, we represent it with an arrow, okay? Which you've done before. You've done this somewhere along the way. So, we show the magnitude and the direction. So, if I have a force that's 2 newtons to the right, I will draw it as an arrow. Now, you would use a ruler, okay? I can't on the board. It's going to the right, so I have the arrow going to the right, and then I would say it's 2 newtons. Now, depending on your questions, you can do these by construction, which means I want them to be at a certain length, so I'll give you a scale, or it's just a representation. So now we've got to be careful. If I want to draw another vector that's, say, 5 newtons, but in the same direction, I have to draw it longer. Okay, it doesn't matter that it's not exactly double, it's just longer. It's just showing the relative size. Okay, so that's important. Then we get 2 other ways of doing it, and here we've got to be careful with the terminology. So we can draw force diagrams. Now, force diagram is where we take whatever our object is and we draw it as a box. Now, this is to help people like me who has no artistic ability whatsoever. So if they tell me I have an elephant and I want all the forces on the elephant, I can just draw the elephant as a box, which is good because I can't draw an elephant. But what we do with the force diagram is we show the forces acting on an object exactly how they act on the object. So if it's a push, we show it as a push. If it's a pull, we show it as a pull. Okay, so that's very important. So for example, if we put a little box over here, okay, so that can be anything. It could be me, it could be a chair, it could be whatever. I can show that my box is being pushed. And I can show that there's the normal force. So I'll show it exactly how it's shown. So the normal force is from the surface upwards, okay? Gravity on this one gets shown from the middle. And it's always shown from the center of gravity. That's quite important, okay? So for a force diagram, we always draw it this way, okay? Free body diagram, now we get to the fun part, because now free body diagram, we draw it as a dot, but the arrows point away. So same here, now I've got my dot, okay, so it's the center of gravity, arrow goes up, that's the one that was going up, arrow goes down, that was the gravity, but now this pushing force gets drawn like that. So we draw all the forces going away on a free body diagram. We'll talk about labeling later, okay? So, these were our key words that we've looked at so far. Force, contact, contact force, non-contact force, and Newton, okay? So we've done quite well. We've done lots of little bits and pieces. And that's where we're going to stop for now, and we'll carry on in a second. Welcome back. So before the break, we did a little bit of an overview. So we looked at properties, we looked at types of forces, and we looked at representation. Now let's be a little bit more technical, okay? Let's get into the nitty-gritty of it. So what we're going to do is we're going to now talk about what happens when you push or pull an object, okay? So we're going to go to a bit of a simulation, which is great because I can't draw. So there we go. So here we have our little man, okay? And what we're going to do is we're going to start applying a force. Now here, I haven't got friction. We're ignoring friction for now because it's going to be a bit easier. And I want you to see the speed. So it's going to be a little speedometer. That's just going to show you how fast it's going to go. Watch. I apply force. It's not in fact, it's zero. Nothing's happening. He's not pushing, he's just standing there. Okay? Pushes a little bit. So we apply a little bit of a force, and you can see he starts moving. But can you see, if you look at the speed, he's getting faster and faster and faster. But he's pushing the object. Okay? If I make this force smaller, now his force is zero, it still keeps going, and it keeps going, and it keeps going, and it keeps going. It'll keep doing this. There's no friction. Now, hopefully, I can apply the force again. I apply the force, what happens? He starts to speed up again. So, if there wasn't a force at the beginning, so we're going to reset it, okay? At the beginning, object wasn't moving. Then we had to apply the force, okay, so we had to give it some value, and then the object could start moving. So we could speed it up. If I took the force away, it still keeps going. If I want to change the motion, I have to apply the force again and make it go faster. Okay? So the force did two things. Started it moving, and then it could make it go faster. But, there we go. But, that's only force in one direction. Let's play some Tug of War, which is over there. Okay? We have our men. Let's put a speedometer. There we go. That's the word I'm thinking of. on our little object. There we go. So I'm now going to put a man on the rope. Nothing's happening. Object is stationary. Now we're going to let him pull. So it's like tension. This force is a tension force. There we go. And he pulls. What do we see? The force, let's pause it. The force is to the left and the object moves to the left. So instead of going to the right, like we saw in the first one, now it's going to the left. Okay? Let's put a force on the other side. Let's see if we can change the object's motion. So we could see, if I just leave this here, it was getting faster and faster. Okay? Now, let's put another man. Now he's the same size. So what the animation is trying to show you is because the guys are the same size man has the same size force. Okay, so that's important. Now watch, and I'm hoping he doesn't go off the screen completely. Oh, and if you look there, oops, he had to stop. Now this is quite important. They went for a while, and then it stopped. Why did it stop? Here's another force. So this little block over here is a force. It stopped it. So it was moving, then it stopped. Okay? Let's start again. Now we have them, equal forces on both sides. Watch what happens. Oh, look. Nothing. The forces are equal, so we're experiencing a force, but there's no change in the motion. Let's make the red guys more heavier. There we go. So the force, now they're going to go to the right. I've stopped it. Now I've got enough time for you to see. There's the speed. Okay? I'm going to put another one here. Equal forces on both sides now. Okay? Just like right at the beginning. But it was already moving. So what happens here? Now the speed doesn't change. The speed stays the same. Still moving though. So the forces are being experienced. So what we've done is we've changed the motion. It was getting faster towards the right. Now it's going the same speed towards the right. It's not getting any slower or faster. I'm going to put one more. Now I'm putting a big guy on the left. Let's see what happens. It slows down, stops. Did you see that? It slowed down, stopped, and now it's changed direction altogether. Okay? So what did we do with what this has shown us? The force can start it moving, the force can make it go faster, and the force can make it go slower. So those are the things the force can do. This animation unfortunately doesn't show me the other things, so let's go there. Okay, so we're still on properties. We've done this, we did that earlier. So over here, what can a force do? A force can cause an object to start moving. We showed that. It can make an object slow down, speed up, or stop. And these are all good things. It can also make it change direction. Now that we saw when it slowed down, remember with the two, when we had the nice big blue one, it slowed it down, it stopped, and then it changed direction. It doesn't always have to be horizontal. It's like when you're driving in a car and you turn the corner. You've changed direction, you've applied a force to the wheels. It can also change a shape. Like when you were little and you played with Play-Doh and you squished things and stretched things and changed shapes. That's all forces. It can also cause an object to rotate. As in a car, when we put the force on the wheels turn. That's rotating, okay? Or if you're playing cricket, spin bowlers, they make, with the way they bowl, they make the ball spin, which is important, so it's rotating. So we can do all of these things with the force. You've done that before. Okay, so let's do some questions just to make sure we're on the right track, okay? I want to draw a force diagram of a person pushing a box to the right. We're not going to worry about the person, but what I want is I want all the forces that are acting on the box. So now we're going to have to think a little bit, okay? So, force diagram means we have to have a box. We have our box. Person is pushing it to the right, so we've got to remember which way is right. It's that way. Okay, that would be a basic diagram, but we know that there's going to be gravity. Gravity goes from the center down, okay? We know there's going to be the normal force, which goes up like that. I didn't tell you whether there would be friction or not, okay? So you need to be careful with questions like this. Don't make an assumption about something. So here I'm saying just draw a person pushing the box to the right. Don't assume there's friction. In your exams and tests, they'll always be specific. Okay, yes, there's friction, no, there isn't. Sometimes we ignore friction because it makes life easier. So we're going to ignore it for now. But I never leave a diagram like this. I've got to label it. So this is my normal force. F with an N. This is gravity, Fg. And this is my applied force, my pushing force. Okay? We usually put a key because there's different ways that we can write these symbols, which you may have seen. So Fn can also be written as just a capital N, and that's the normal force. So you may be using a capital N, you may be using Fn, it doesn't matter. But this is the normal, okay? Fg, which is weight, can also be written, now you need to be careful with this one, as a lowercase w. Okay, I don't like teaching my learners to use a W because sometimes it looks like a capital W, and capital W is work. It's a different thing altogether. So it's got to be little w, okay? And that's weight or gravity. Whoops. Then there's F. Here, you may sometimes see it as FA, so you might go F applied, but you need to be specific when we label this one. So this one, you can't just say it's an applied force. It is an applied force. But what we actually have to say is we have to say it's the pushing force. It's the box, it's the person pushing the box. Okay, so you need to describe to me what the applied force is. Where is it coming from? So here, I would put this as the pushing force. That's an I, by the way, pushing force. Okay, don't just say applied force. Why do we put the key? Because we can use different symbols. Okay, and all the symbols are right. We just got to make sure that whoever looks at our diagram is on the same page. Okay? All right. So, force diagram. Now I say to you, draw a free body diagram. What was the difference? We said right at the beginning, force diagram was the box. Free body diagram means a dot. I prefer free body diagrams. So here we have my dot, okay? The first two forces are easy because there's my normal, there's my gravity. Remember, I said when we draw forces, the size of the force is represented by the length of the arrow. So when we draw diagrams like this, if two forces have to be the same size, which these normally are, the normal and the gravity, we should draw them so they look like they're the same size. your examiner is not going to take out a ruler and measure it, okay? But if it obviously doesn't look the same, then there's a problem. So just make sure they look like they're the same size. Now we've got to be careful, because we said there was a pushing force, and our temptation with a free body diagram is to draw it here, because it's pushing. But free body diagram, the forces must be away from the dot. So what we've got to do is take this arrow and put it on the other side. Okay, so I'm going to take it out from there because that's wrong. Okay, and what we need to do is we need to draw it there. Now, the reason why we do free body diagrams is because when it comes to our calculations, these are actually more useful for us. So when it comes to us needing to find net force for Newton's second law a little bit later on, this is useful. When we just have them shown exactly where they all go on the boxes, we can get a little confused as to what goes where and what belongs where, and it gets complicated. This is just better, okay? So, we're going to take another little break, and then we'll do some questions. Welcome back. So, we've done some basic stuff. We looked at some theory. We did a little bit of investigation last time. So now we need to do a question. So we're going to put all the stuff we've learned together in one question. Okay? So again, we're still looking at properties, types, and representation. Okay? So, there we go. Let's see. So here we have a man on a motorbike. Okay, and he's riding north. Very important, they say to me, at a no, that's not what I wanted. There we go. At a constant velocity on a smooth road. So there's a couple of very important things just at the beginning. Number one, they're saying to you he's going north. Now here you need to be careful, because if you look at the diagram, he's going to the left. But remember, just because he looks like he's going to the left doesn't mean he is going to the left. I'm telling you in the question that that's north. So we need to be careful. Any direction that I use, any direction that I describe can be north or south. Okay, so north would be to the left on this diagram, south is to the right. You must look at what they gave you. If I didn't put north there, so I just said a man rides on his motorbike, then I can describe it as going left, but I can't describe it as going west, because that's just the way we drew the diagram. I don't know if west is that way, but he's definitely going left as I look at him. Okay? There we go. Now, he's going at constant velocity. He's not accelerating. That also tells us that it's the same situation as when we had the two men pulling the tug of war, where when the forces were the same, they went at constant velocity. Okay, so what am I telling you? The forces that are pushing the motorbike forward and any forces pushing the motorbike backwards are the same. Okay? Smooth road. Smooth tells me there's very little or no friction. Okay? Now here, because he's going at constant velocity, there's going to have to be friction. Okay? There will have to be friction, so we're just going to go with it. But smooth road, smooth surface, no friction. Why do we put no friction in? To make the question easier. Okay, we're going to add friction. It's just the beginning. So, first question says, indicate the following forces on the diagram. We like questions like this because they say use the diagram, don't have to redraw it. Basically, I'm asking you to do me a force diagram, and I want the applied force. Now here, the applied force is the force from the engine. Okay, so the engine is somewhere in the middle. We're not overly concerned whether you know where the engine is, but what I do need to know is which direction is it going in. So my applied force is going to make him go north, and it's here. Okay, so this is my applied force. I'm labeling it exactly the same way as they told me in the question. Here, I can't make up my own labels. I must use what they told me, okay? Now here we do put friction. I said it was a smooth road. Really wasn't a smooth road. Has to be friction. But this is a force diagram. So now we've got to go, where does friction act? Well, friction has to be on the road, and friction is between the tires and the road. Okay, so now when I draw it, there are two tires. Both tires have friction. So I'm actually just going to draw one. I'm going to draw it, there we go, on there, and this is friction. Okay, just pretend you can read my handwriting. Friction. Okay, so here I'm showing exactly where the friction is. It's between the tires and the surface. Now I want gravity. Now this one becomes a little bit interesting because it's on the motorbike, and the motorbike experiences gravity, the man experiences gravity. So really we could put it in a lot of places, but we're not going to do that. Whenever we put gravity, we put it in what we call the center of gravity. In other words, if we could ignore all the outside, we could say right in the middle, this is where the gravity actually acts at the most. It's not the best way to describe it, but it's the easiest. So I'm going to draw it in one place, and we're going to draw it in the middle. So we're going to put gravity here. Okay, so there's gravity. Okay, in the middle. Then they want the normal force. Now the normal force, remember, is from the surface to the object. Here, I can't just draw one because there are two tires. Both wheels touch the ground. So actually the normal force is between both of them. So I have to draw a normal force over there. I'm just going to draw it out of the box so you can see it. But there would also have to be one there. Okay, and we make sure that they reach the surface. So we've got the normal force. I'm doing it on both because they're both hitting the ground. Okay, both tires experience that normal force. The man's not having a normal force with the ground. Okay, because he's not touching the ground, which is a good thing when you're riding a motorbike, okay? Especially when it's moving. It's not good for the shoes. Okay, so we got that. We've got the applied force, which is going north, so this must be in the same direction. Friction, always in opposite direction. Okay, friction opposes motion. It's not good for it. Well, sometimes it's good, sometimes it's not, depends on the situation. Gravity from the middle, the normal forces from the tires. Okay? First question, we liked it because we didn't have to redraw it. Now they say, draw a free body diagram. Now, we had done the normal force with two things, okay? Here it's going to be a little different. Free body diagram says that we have to have a dot. So here's my man on the motorbike. It's great, that was easy. We had the applied force, which was going to the left, which was north in this case. We're going to keep the same labels. We can't change the labels. They told us what they had to be, so we've got to keep that, okay? Gravity goes from here, that's nice. And that was Fg. Now here, I'm not going to do 2 lines for the normal force, because I don't have to. Because here, I'm putting everything together as one object. Because I'm doing it as one object, it means I can just draw the normal force like this. Free body diagrams are so much easier. So much easier. The other one we needed was friction. And there's my friction. So if we now look at this and we go, if I have to do a calculation, if I have to do a description, this is much easier to work with because it's simple. So free body diagrams simplify things for us. But you need to be careful. You must read the question in front of you, okay? Because if they ask for a force diagram and you give them a free body diagram, you lose marks. If they ask for a free body diagram and you give them a force diagram, you also lose marks. So just be careful, okay? Nice and simple. Let's add some stuff into this. Now they say, what do we know about the forces applied and friction? So what they're asking you here in a roundabout way is, what is the relationship between them? Is the applied force bigger than, smaller than, or equal to friction? Okay, so we've got to go back to the beginning of the question where they said he's going at constant velocity. So remember, constant velocity, I said to you right at the beginning, means it's like the tug of war, they're pulling at the same amount. That's the only way that can happen. That means that force applied and the friction are equal in size. I didn't say equal, okay? Because equal, because force is a vector, means that they're equal in everything, size and direction. But they're not. They're equal in size, but opposite in direction. So they go in opposite directions. They balance each other out. Okay, that's what they're doing. Then, now, the man pulls the accelerator levers. Same as in a car, pushes his foot on the accelerator. The motorbike starts to accelerate. Velocity is not constant anymore. He's now going faster, and he's going to be going faster north, okay, and to the left as we were looking at the diagram. This is the accelerator, not the brakes. Which one of the named forces, so remember the named forces was applied force, friction, gravity, and the normal force. Which one of them increases? So we've got to think about this and go, what direction were they all moving in? Gravity and normal were vertical. They've got nothing to do with the horizontal motion. That means it's either the applied force or it's the frictional force, okay? Friction will slow him down. So by pulling the acceleration levers, he's increasing the applied force. Okay, he's increasing the applied force. That makes him go faster. We're not worrying about what happens with the friction. We're going to deal with that later. Now, he starts to accelerate. We've actually answered these questions. Does Fg also get bigger? Fg is his gravitational pull. How hard the earth is, or how big the pull of the earth is on him. Did his mass change? No, unless he was eating while he was riding. Did the motorbike's mass change? No. So it can't be Fg, okay? So this answer is no. Okay? Does his normal force change? Well, the normal force is related to gravity. So if his force on the earth didn't change, stayed the same size, normal force also stays the same size. So this is also no. This is very important. Just because we changed one of the forces doesn't mean the others also change. And for us, when we look at forces, mass is a constant. Okay, we keep mass constant because it makes the maths easier for us and it makes the questions easier. We're not trying to trick you. We're not trying to make it more complicated at this stage. We'll do that at varsity. Here we're trying to keep it nice and simple. Okay, so mass doesn't change. That means gravity is not going to change. Okay, we can change the normal force, but we're going to look at that later. For this, we're not changing it, okay? So, what have we learned today? Okay, because there's things, we need to just summarize it. Number one, a force is a push or a pull, and it is a vector. And we remember, vector means it has size, magnitude, and direction. Also means when we do that, when we do questions with forces and we have to calculate a force, we need to say which direction the force is acting in. Okay, very important, don't leave those out. A force can be a contact force like friction, tension, the applied force, the normal force. There's lots of contact forces. Or it can be a non-contact force. Gravity, magnetic forces, electrostatic forces, okay? In this section, when we look at forces, it's part of mechanics, we're only going to worry about gravity, okay? We'll deal with electrostatics later, and magnetic, you'll also deal with later. We're not going to worry about those. Forces are measured in newtons, okay? Newton, remember capital N, and when we write it down, because it's the surname of a scientist. Okay, forces are represented by arrows in force or free body diagrams. Remember, force diagrams have to have boxes. Okay, free body diagrams have dots. Okay, and I didn't write them out because we like to learn with pictures. Force diagrams, the forces are drawn exactly as they are shown. So if it's a pushing force, we draw it as a pushing force. Okay? Free body diagrams are drawn with the arrows pointing away. That makes it a little more complicated for us, but they're always pointing away. They go away from the center of gravity. Alright? So, we've done a lot today. Okay? We've done properties, types, and representing force. Next time we're going to look at components. I'm going to make it a little bit more difficult for you. But that's all we've got for this one. We'll see you next time.